Hello everyone, my name is Alex, and today I'm going to talk about our CVPR paper, Multidimensional Vision Model Pruning with Latency Constraint. So in recent years, we have seen a trend of exponentially increasing model size. And on the graph here, you can see how the trend looks like. With the emergence of complex model architectures such as transformers and large language models, the number of parameters of the model quickly explodes and even reaches trillions of parameters. Such large models lead to huge energy consumption. And deploying these large models also becomes a challenging task. For example, when we want to use the model in edge device, directly importing the model to the device might be infeasible due to the limited storage and memory. And the edge device applications such as autonomous driving usually have the requirements of real-time response. Therefore, reducing the model size and improving the model efficiency is very important. When it comes to the cloud computers where there is huge compute capability, we will still favor an efficient model to make sure the service is always online for more users. This is why model compression is needed. Model compression has become essential for reducing model size and energy consumption, and also the inference latency while preserving the performance. And among various model compression techniques, pruning has been a predominant approach. Pruning generally, pruning involves removing redundant parameters to yield a smaller and more efficient architecture. And like nowadays, pruning methods face several key requirements. They must be hardware aware to optimize for specific deployment platforms, support transformer-based architectures, and also remain effective under aggressive pruning ratios as model sizes continue to grow. So before introducing our approach, we want to first review some key pruning concepts. Pruning reduces model size by removing redundant parameters from the dense network, resulting in a more compact architecture. And one common category is unstructured pruning, which eliminates individual parameters without considering their positions in the network. However, such unstructured sparsity is difficult to leverage for practical speedups on standard hardware and often requires specialized accelerators. Another category is called structure pruning, which enforces structure sparsity by removing the entire units, such as convolution channels or transformer heads. This leads to compact and hardware-friendly models that enable practical inference speedups. And in this paper, we will mainly talk about structure pruning. For the majority of pruning methods, parameters are first ranked based on an importance score. Then the lowest ranked ones are removed during the pruning process. There are several different kinds of importance criterion, and the magnitude-based score is very intuitive, where the weights with smaller magnitude tend to have smaller contribution to the outputs, thus would be less important. And the other commonly used criteria is gradient-based score, where the importance of a parameter is measured directly on the loss change induced by deleting that parameter. Gradient-based score is shown to be more reliable than magnitude-based score. And this example here shows the gradient-based importance score proposed in a CVPR 2023 paper. The authors in this paper introduced a Hessian-aware metric that assigns global importance score to transformer components, such as queries, Ks, and heads, based on the loss increase caused by their removal. And in our paper, our framework also adopts this importance score in our transformer experiments. The other things that we need to consider, especially for the mobility applications on edge devices, is how we can maximize the GPU compute to get and obtain a fast or real-time response. On GPUs, instructions are executed by the streaming multiprocessors, splitters into waves for parallel compute. To fully utilize the GPU compute, it would be better to occupy 100% of the streaming multiprocessor. As different GPU architecture vary in number of streaming processors, as well as in cache and memory, we need to adapt our model accordingly, specifically for the targeting hardware device that we want to deploy the model on. However, it is not that straightforward. In transformers, for example, computation cost is influenced by multiple interacting dimensions. As illustrated in the diagram here, a transformer block's latency depends on factors such as embedding size, number of heads, query and key dimensions, value dimension, and also the MLP linear hidden size. Accurately modeling latency, energy, and other performance metrics across these dimensions is critical for effective pruning, but this poses significant optimization challenges. Another challenge, as mentioned earlier, is the exponential growth in model size, which demands more aggressive pruning to achieve higher pruning ratios. Pruning only finer-grained components such as channels or KN queries is no longer sufficient. To scale effectively, pruning must also simultaneously support removing parameters at higher granularities, such as entire blocks. To tackle both challenges, we propose our method MDP, a unified pruning framework optimizing for the true hardware latency across all model dimensions and multiple granularities. While this presentation focuses on transformer, our method is also applicable to convolution networks. The first step in our method is to identify prunable dimensions within the network and encode them using one-hot vector variables. And in a transformer block, there are 5 such dimensions. The one-hot index of each vector variable would encode the total number of parameters retained along that dimension. For instance, if the query dimension is encoded as 0010, then it indicates that 3 out of 4 queries are preserved. We also encode block level decisions using binary variables. If the variable for block decision is 0, then this entire block is considered to be deactivated, and all associated prunable dimensions are ignored. Only when the variable is 1 do we consider pruning within that block across this defined prunable dimensions. Then the next step is to define the latency function, mapping different configurations to the inference latency. This would allow us to get the pruning processes for practical speedups. And before setting up the function, we first prepare a latency lookup table, pre-computed and prepared on the target hardware. Within a transformer block, based on how each component is characterized by the dimensions, we prepare 3 latency lookup tables. For example, in the QK latency lookup table, the first entry 0.04 in this first cell represents the latency when the block has only one head, like when the transformer block only has one head, one query, and an embedding size of 1. Using these prepared latency lookup tables, we can thus set up the latency constraint function, mapping from the prunable dimension variables to the inference latency. And in addition to the latency function, we also define an importance function to capture how different pruning configurations impact model accuracy. For transformers, we begin by computing the Hessian-aware importance scores discussed earlier to score all components. We then perform a sorting and aggregation step to determine the importance of retaining a specific total number of parameters along each dimension. Combined with our variable encoding, this allows us to construct the importance functions as shown here. With both the importance and latency functions defined, we formulate pruning as a mixed integer nonlinear program, or MINLP for short. The goal is to maximize the importance objective while ensuring the latency function remains within the budget size. The final prune structure is determined by the selected values of the prunable dimension and block decision variables. Here, we quickly present some empirical results demonstrating the effectiveness of our method. Applied to both CNNs and transformer architectures, our approach consistently achieves better accuracy and latency trade-offs. And we also compare to previous state-of-the-art methods, and we can say that MDP outperforms them by a clear margin across all the evaluation settings. Thank you for your attention, and if you're interested in knowing more about our method, feel free to scan this QR code or send me an email if you have further questions.